yes, thanks for that warm welcome. As Anthony said, my background is not, I'm new to the cryosciences community, and I hope to bring some expertise in computation, computational methods, physics, but I'm very much eager to learn from all of you about the domain science that's being done with these data. Today, we'll be talking a little bit about the computational machinery. I'm wondering what works better, whether to, I'm going to present both. We'll see if that works well. And so we're going to be talking about a pretty foundational tool for collaboration in modern computing, which is the version control system Git, and its use combined with a platform like GitHub. GitHub is not the only one. There are other online services that facilitate the same kind of Git-based collaboration. We happen to be using GitHub, but you're welcome to use other systems such as GitLab or Bitbucket. I want to thank first of all, Jane and Anthony, who have done a huge amount of work in setting not only the entire event, but also the mechanics of running this online, and they've had to put a crazy amount of extra work in the last few weeks. So I'd like to thank them, and also the team who is teaching with me. We've been trying to prepare this for the last few days. So in order to talk a little bit about, oh, sorry, I went out of present mode. In order to talk a little bit about Git, first I want to at least briefly describe, and I know that you've already been testing connections and whatnot, but I want to briefly describe sort of the tools that we are using. And those tools are the online tools that we're going to be using are based around two pieces of machinery that actually come from our community, Jupyter and Pangeo. So let me very briefly, we'll talk more about Jupyter and Ipython in the later tutorial today. So very briefly, I want to explain what Jupyter Hub is. Jupyter Hub is basically infrastructure to host online on any shared, basically shared server resource, which could be a beefy computer on your desk that your research group uses to log into, or it could be a supercomputer at NCAR, at NASA, at NERSC, at any supercomputing facility you have access to, or it could be a set of servers in the cloud. But the idea is to offer server-based machinery that allows you to use the same Python and Jupyter tools that you would install on your local laptop, but to use them on a remote resource where you have to authenticate. So the idea is that you have a shared resource somewhere that is potentially more powerful than the machine on your desk or your laptop, or that is closer to the data that you want to use. And Jupyter Hub is effectively a set of interlocking pieces that allows you to authenticate into that shared resource. In our case, we use authentication via GitHub, and Jupyter Hub has been designed to be very modular. I won't go into architectural details. The point is, it allows you to somehow, whether it's because you have a local account on that system or because you use an intermediary, such as, let's say, your GitHub ID, you can log into that server. And then that server exposes fundamentally two things. It exposes user interfaces that are web. Obviously, they have to be web-based, but there's more than one. We're going to be talking briefly about the one we'll be using mostly, which is Jupyter Lab, but you can actually deploy in front of it other sets of tools that are accessible through the web, such as our studio, such as Visual Studio Code. So you can effectively these days replicate more or less any desktop environment or any desktop tool, almost any desktop tool that you want through the web. And those are meant to be interfaces into some computational engine, basically. And for that, Jupyter has support for many programming languages. The name is inspired by Julia, Python, and R, which are sort of the three open languages of modern data science. But Jupyter actually supports many more languages. We'll talk a little bit more about that later. And so the idea precisely that Jupyter Hub is a connection between these three pieces: computational systems, basically sets of programming languages, libraries, and tools that execute your code that are available to you to be viewed through one or more interactive interfaces that let you access code, data, visualize, etc. And that allows arbitrary users to connect into the shared service, which can have both compute resources and data. Now, Pangeo is a project connected to Jupyter, but that was independently developed by some members of this community who are here today, as well as others that we are connected with. And the idea of Pangeo is to basically deploy these kinds of shared services in the cloud but not only using Jupyter, actually connecting with other tools, in particular Dask, which is a tool that assists in distributed computing, in trying to make common tasks in distributed computing easy and operable and easy to perform, basically with high-level primitives that are sort of for regular scientists who want to do analysis workflows, don't require you to become an expert in parallel programming. Underlying that is a set of packages called Xarray, or a project called Xarray, which effectively takes the NumPy model of dense numerical n-dimensional arrays, but adds a layer of data semantics, labeling, and more sophisticated data description operations on top of the core numerical machinery that NumPy exposes. Xarray effectively exposes the netCDF data model and connects it. It's sort of, in my mind, a marriage of the netCDF data models, some functionality that is very pandas-like, and the traditional core array machinery of NumPy. And so Pangeo is a community-driven project that basically combines the idea that good numerical access tools combined with good distributed computing machinery, combined with a high-level interactive interface, are exactly what's needed to do collaborative, large-scale data, modern data analysis in the cloud. And for the sake of time, I'll skip on the video. You can take a look at it later. So this is going to be a quick review of steps that you should all have been able to take by now. If anyone is stuck, if anyone has an issue with these steps, please ask on the questions channel and we will help you immediately. You should have been able to log into the Hackweek Pangeo hub with your GitHub ID, and you should see a screen like this one. After you, I'm sorry, these two slides I just realized were reversed. This is the landing page that you should have seen. I'm sorry about that. I need to correct that on the slides. So when you go to this URL, you should see this this landing page that tells you that this particular Pangeo hub we're using is hosted on the Amazon cloud in a particular region. And I'm getting a little bit of input here on the. Anthony was saying that there may be some delays for some of you. Oops. So I will we'll take a second to pause at the end of the section just to make sure that everyone is on the same page. So this particular Pangeo hub is hosted on the Amazon cloud, but Pangeo is a platform agnostic set of computational tools that can be deployed on other cloud resources. Once you sign in, you should see this screen. In this particular deployment of the hub, there's only one option. Sometimes you have a collection of options of either how the images are, these virtual computers are configured, what libraries they have installed, or what kind of hardware they have access to. For example, whether there's a GPU available or not, whether there's more or less cores or RAM, etc. So you choose your option. In this case, there's only one. And when you click Start, you should land on an interface that looks like this. And we're going to talk about this for a second, but I want to take this pause. If anyone is not seeing something that looks roughly like this and you're having login problems, or there's a bit of a delay after you click here Start and you're seeing a little bit of a delay, we will pause for a minute.
And I would suggest, Fernando, that maybe we ask people to put a yes or a no in next to their name in the participant window to indicate when you've successfully gotten onto the hub. So if you've gotten onto it, put that green check mark. If you're having some trouble, put the no, and then we'll get a good poll of where people are at.
The little box and we'll go and help you. Okay, so I see a couple of no's. We're going to be a little bit slow for a few minutes just to make sure that folks have a chance to catch up, because obviously the rest of the tutorial we want everyone to be following along with us. So I'm going to take just a minute to make sure that we can help you, and we'll because I still see a few no's. For those of you who put a check mark with a no, you can ask on questions and we can try to help you, and or in private chat. And but we would like to ask you that you update the no to a yes so that we know that you don't need help anymore. Because we do want to make sure that we don't leave folks behind. And if somebody hits a bit of snag that's taking longer to resolve, we will work with you to help you catch up. I'm going to wait maybe one more minute, and then we'll continue. I'll reorder. This slide was meant to be here in the meantime. Okay.
Seeing about 10 no's so far, Fernando. Wondering if some of this might just be slow deployment of the hub. It does take a little bit of time. If not, if it's something not related to that, feel free to send us a question in the Slack.
Okay, and we'll continue. If it's true that sometimes it does take a couple of minutes, and especially if the system has to basically spin up a new virtual machine, it will have you waiting for a few more minutes. Whereas sometimes if you get in and there's a virtual machine that's already been spun up, you get in more or less instantly. So there's a bit of variability in that. So okay, so I'm going to continue for the sake of time, and hopefully people will gradually catch up. We'll try to help everyone on the Slack channels. So what you land into, and we'll talk a little bit more about this afterwards, is an interface called Jupyter Lab that is developed by members of Project Jupyter. And the idea of Jupyter Lab is to give you a very flexible and very modular and extensible environment, basically for kind of modern data science. It collects a lot of experience that we've accumulated over the years being users of Ipython and Jupyter. And I'm only briefly going to describe enough of it now so that you get your bearings as you use it today. And we'll talk a little bit more in detail about more pieces of Jupyter later today. And the idea is to give you basically all of the tools for everyday scientific computing in one location. It runs the same on your local laptop or on a remote server, and that's very nice because you get kind of uniformity of a complete environment. So just to help you get your bearings on the screen, the screen that you get at the beginning looks kind of like this. And the areas are, the key areas in addition to kind of a standard menu bar, are this left side bar that allows you to click on each one of these icons and gives you a different kind of tools, these sidebar tools. The default one is the file manager, that is just your standard kind of file navigation tool that if you're in it, you can delete it, etc. And it shows you basically files that you can open. There's also, there's also a tool for seeing running processes. So as you begin starting computational processes, these are listed there, so you can go and stop things that you don't need anymore. There's a command palette. Basically, all of the system within Jupyter Lab is accessible via commands that you can type, and this gives you access to those. An inspector for object details, a list of open tabs that you may have, etc. And as I said, it's an extensible system. So this particular screenshot was taken on a machine where I had one extension added for tables of contents that shows me an outline of a document, but you can have more extensions included here. In fact, the hub that we're using has a slightly different set of extensions. The main launcher here gives you tools to start new processes. We're going to focus right now on opening terminals and notebooks, which we'll see in a minute. And I'll talk a little bit about these other tools later on. Now, this is what Jupyter Lab looks like when you have a few more things open. And importantly, all of these little tabs can be dragged around. So the idea is that within one screen, you can put next to each other. Effectively, the tools that you would have on a desktop fit here on a tab, and that workspace is preserved across time. And so it gives you a view into all of your computational tools. And you can have what we call Jupyter notebooks. Most of you are probably familiar. For those of you who aren't, they're basically documents that combine sort of standard text and graphics with code and the results of the code. You can have what's called a console, and a console is another computational view tied to the same data, but that is not within the same document. So the idea is that you can view the variables and do computations with it, but without leaving a written trace of it in your document. I think of it mentally as having my main write-up and scratch paper, where I'm thinking about the same computations, but down here in the console, I may do work that is just throwaway. I want to check something, but I don't want it saved. And in the main notebook is where I keep the things that I want written down and preserved as I save them into a file. This is a file, and here there's no file. It's only the computations and the data. You can have text files, Python scripts, Python scripts, markdown files, etc. And you can have terminals that run on the same host that you're logged into, which is very convenient because it means you don't have to configure remote SSH access and whatnot, which can be actually quite complicated if you're working in the cloud with hosts that change locations all the time. And so this gives you, just with one click, you have a terminal, a full-blown terminal connected into the system. This could be, in this case, this screenshot was taken on my laptop, so that terminal happens to be on my local Mac. But once we're working remotely, we'll see the exact same thing on the remote hosts. So what we're going to do now is actually grab our tutorial materials to get started. So those materials live on GitHub. And we're going to, there's a bit of a bootstrap problem here. We haven't talked too much about Git, but we need you to do one thing. So we're all going to do, now I am going to go to my Jupyter Lab instance, right? So this is my actual Hackweek and GeoHub instance, and I don't have anything. So the first time you log in, the only things you should see are these two directories that are two folders we've created for you where we have shared data. You can share data with others by writing to the shared area. And we also have data for the tutorials that is available for everyone to read easily. So if I click here, I will get a terminal. And so this is what my terminal now looks like on the system. This is my location on the system. These are those two folders that you see there. And what I'm going to ask you to do is to type into a terminal this command. We're going to type git clone and that URL, which is copied on the slides and is copied on the README of the tutorial as well. So you can copy it either from the slides or from GitHub, or you can read it from the screen. And as I hit enter, what happens is I now have content. This takes a second to refresh, or you can force it to refresh by clicking here. And now you see that I said I want to clone this data from Git. From GitHub, a tutorial called Intro Git, and now I have something called Intro Git that is available here. So everyone should be okay up to this point, and with the Intro Git tutorial cloned into your Hub instance. And if we got here successfully, that's great. If anyone has problems, please ask us. And now I'm going to stop sharing and hand it over to Fernando Paolo.
Okay, thanks, Fernando. I'm gonna share my screen right now. Okay, can everybody see?
Yeah, and I'll just ask Fernando Pérez. There we go, just muted. Thanks.
So we're gonna go now quickly through the very basics of the command line, and that is the terminal. So Fernando just showed how your main Jupyter Lab landing page looks like. Is here. So everybody then already cloned the intro to Git repo. Now let's click on it on the side. So we are inside that repository, and here we can see all the tutorials for it. Now let's open, that is, click on this very last one called Intro Shell. Double click on that. And we have opened now the tutorial. This is a very basic introduction, just to bring everybody to to a similar level. Another thing we can do here before anything else, just click on the top left, this folder icon, to maximize the work area. All right. Okay. Let's start by defining two main basic concepts. First of all, one is the shell. What is the shell? Right, so the shell is just a program that takes commands from the keyboard and gives them to the operating system, right? So the shell is a layer that allows the user to directly interact with the operating system. One way to think about the shell is think of your operating system as a onion with several layers, right? The innermost layers are the kernel of the operating system. So the shell will be the outermost layer of your operating system. And outside this onion, outside the shell, there are all the applications that we have on our computers floating around. The web browser, the PDF reader, our email client, desktop, you name it. So these applications, they interact with the operating system and vice versa through this layer called the shell, which is a program. So we're gonna refer to it as bash because bash on Linux systems is one shell. So there are different shells. You can think of it as an analogy, all the different web browsers that we have, right? Internet Explorer, Safari, Chrome, Mozilla, they are all programs to interact with the internet. Well, with the shell is the same thing. Bash is one of those shells to interact with the operating system. And it turns out that on Linux machines, it became a default. That's the only reason we are using bash. So the second concept here is the terminal. The terminal is yet another program that all it does is open a window that allows you to interact with the shell. So again, like the shell, we have different types of terminals, right? People by preference choose one or another, but the purpose of the terminal is the same, to enter shell or bash commands that will be targeting the operating system. So whenever you hear command line, command prompt, console, we are always referring to the terminal. You can use those terms as synonyms. Finally, we have the so-called shell scripts. Shell scripts are nothing else than a bunch of shell or bash commands stashed into a file that we can then call from the terminal and execute one after the other or at the same time. So here is a very important concept about the shell. This is my last point. It says, you know, the shell is not only a powerful command line interface to the operating system, but it's also a scripting language. You can do sophisticated processing of information, just like you do with a Python script. You can do with shell scripts. We're gonna see this in a little bit. All right, let's go to the more interactive portion of this tutorial. First of all, we're gonna see some very basic commands here. Let's go to the side here of the notebook and open a terminal. Click on this plus sign. Open first of all. Click on this plus sign here on the navigation tree. Click the icon terminal, and here we have a terminal. So to facilitate things, as Fernando showed, let's drag this tab for the terminal either at the bottom, or you can do that to the side, right? If you prefer to have the terminal on the side there. Let's increase the work area. Okay, I'll leave it like that. So we have the tutorial notebook and the terminal on the same screen. So here I have a bunch of commands. We don't need to run them all. You can come back to the tutorial at any time. But these are the very, very basic commands that we all use through the terminal. The first one is when I know where am I within my directory structure, within my folder. So the first command, pwd, type it on your terminal. That will print the working directory. Here we have home, Jovian. That's your home directory. Second question you might ask is, okay, what do I have in this directory? So then we have list the folder content, ls, type enter. Let me just quickly check here that everybody's doing okay. Okay. So as an example, then we have also flags or arguments to each of these commands that they slightly change the way they output information. So let's go again with ls, now -l, ls list stuff, -l here. Not only will list the content of the directory, but it will also give information about each element on that folder. Right, so we have a bunch of stuff here. You don't need to know the details for now, but we have information about the permissions on folders and directories, the size of it, the user that created those. Okay, another useful thing that I don't have here that I use all the time is clear. I like to clear my terminal every so often. Then cd, change directory. That's the next most basic command, cd. So cd, first of all, ls, to list the directory, right? Let's get into this folder called tutorial data. cd type tutorial data, right? This, let me give you another nice trick here called tab completion. You don't need to type the full command or the full path or the full name of the directory. If you type part of it, tutor, for example, and then hit tab, right? The terminal will complete that for you. That's very easy. We don't need to type all that stuff. So cd, tutor, tab, we have everything, enter, we are inside tutorial data. Let's see what is in there. We have a bunch of stuff, greeting, Northwest, these are folders. Now let's get back where we were. There are two ways we can do that. One is cd ... That will take you back one folder. Or, very useful, cd without anything, which is the same as cd tilde, right? It's easier without anything. That, click enter, that will take you always to your home directory. pwd, we are again in home Jovian. ls, we are again on our home directory, right? cd nothing means wherever you are, it will take you back to your home directory. Okay, let's keep going. Let's skip some commands. The next one here, echo. Echo prints stuff on the screen. So I have a string here. This is a text, echo, and there it is. It prints that for me here. This is a text. Another thing I can do is say, echo, this is some other text, but now I don't want it to print it on the screen. I want to dump that into a file. Let's do a greater than file.txt, and we have nothing on the screen. Let's type ls, and we now see that we have created a file.txt. So yet another command, very useful, is cat, which will show us the content of a text file. Let's do cat file tab to complete file.txt. And here we have, this is some other text. So cat shows the context of a file. Other commands, very useful, make dir, will make a folder. Let's make dir and a folder called test. Click enter, click ls to see what we have. And we see that now we have here a test folder. And then we can remove a file, remove file tab txt, we remove the file, or we can remove rm dir our folder. ls, both of them have gone, right? So you can go through these commands later on. We just, let's go farther down to the actual notebook cells in here. So the question now is, can we type these bash or shell commands directly on a notebook cell? The answer is yes. All you need to do is to put an exclamation point in front of that set command, and that will tell the notebook, hey, do not interpret this as Python code or Julia or whatever. This is bash. So here we have exclamation point pwd, and let's see what happened. There it is. It shows us where that particular notebook where we are typing on is. It is in home Jovian intro git. Now let's see what ls-1 tells us. This is listing the content of that folder. -1 says just print this on a vertical structure, which is easy to read. Echo, same thing. Remember echo prints on the screen? Well, now it prints on the output of the notebook. Next, and almost getting to the end, is there another way that we can tell the notebook that all our shell content, all our cell content is also bash or shell commands? Yes, and that's called this bash magic tag, which is %% bash. We place it right on top of the cell, and then we can write a bunch of operations here that you don't need to know exactly at this time what they are doing. You can come to them later, but these are all command line operations, one after the other. And I dumped all of them on a single cell. I'm gonna execute that cell, and I have a bunch of stuff being performed. So the notebook knows that all these are shell or bash commands. And finally, to end, we mentioned about shell scripts. right? So I put many commands, the commands I just showed to you, on a file called commands.sh. So let's see what is inside that file. Exclamation point cat commands sh, and we see here that we have a bunch of bash commands. So let's execute that file that will fire up all these commands. And here we call shell script with this sh and then the script. This is the same as calling Python program.py. Here we are doing bash commands.sh. And there you have a bunch of stuff being executed as a shell script. So with this, I will end this repository. Just point out to you guys that here you have a very nice, click on this link, summary of the most common bash commands, all separated by category, the command on the middle column, and the explanation on the rightmost column. So this is very handy. And with that, I will pass it again to Fernando Pérez. Thanks. Let me get out of my sharing.
Thank you, Fernando. For that, let me start sharing now. I'm lost in a sea of windows all alike. All right, here we go. Share. Okay, you should all be seeing my. So here I have a terminal open, which Fernando just explained. By the way, in my case, I had switched my settings to have my terminal be black. You can change that here. The terminal can be chosen to be light, like Fernando had, which I believe is the default, or dark, which is kind of the background that I'm used to. So I've already cloned the Git repository that Fernando was showing. As we discussed earlier, it seems like folks are mostly caught up from the marks on the Zoom call. So let me double click on that intro Git directory. And here we have the contents of that repository. And what I want you to do is I want you to click on this notebook called index.ipynb. So if you click on that, if you double click on that, it opens that notebook. It shows a green mark next to it, which basically is telling you that notebook is active and open here, which is that the toolbar, the sidebar tool for controlling your running processes. If I click on it, you will see that index.ipynb is now active. It has a kernel attached to it. I can stop that process if I want to. And I have two terminals because I didn't completely close one that I had earlier. I didn't shut it down, which means I can recover it. This is a terminal. The process itself was already open. I can close the window without shutting down the process, and I can reopen it if I have something there that I want to see later on. And so now what we're going to do is use this little index notebook to navigate through the various things that we need. It makes it easy for you to find rather than looking at file names to kind of go in order of topics. So we've already covered these two sections. Now we're going to look at sort of the fundamentals of the version control system Git. I'm going to collapse the sidebar, and I'm actually going to use what's called presentation mode in Jupyter Lab, which is a slightly modified set of font size and display defaults that make it a little bit easier for remote viewers. So for those of you who haven't used it, what is Git? This is a tutorial that is going to hopefully give you a mental model of Git, and it's not original. It's based on a couple of excellent sets of materials that I found online. Unfortunately, the original one, I can't find it anymore, but I've tried to credit its author. Was a tutorial. It was basically the tutorial that moved me from a very sort of memorization-based approach to Git that was very confusing to me when I first started using Git over 10 years ago, to really having a mental model that helped me understand how the thing worked under the hood, which made it much easier to later look for answers, learn more, understand when problems arose, understand the error messages of Git, which are famously cryptic and difficult to understand. And so we've tried to capture some of that in today's tutorial. What is Git? Git will be described by many as a version control system or a source control system. And these are systems that were invented, I believe, back in the 70s for the management of typically originally computer software files. And they are systems designed to track changes in a systematic way that are made to text files. There's issues with binary data in version control systems that are pretty tricky. We won't get too much into that. I'm happy to answer questions about that later. But it basically is a systematic way of tracking how text files evolve over time as you modify them, so that you can move back and forth between them. You can track your changes. You can compare changes. And if you want to have your work be easy to reproduce and easy to share with others, it becomes kind of a fundamental skill that you should probably adopt as an everyday habit. It's not a specialty tool to be used in exceptional cases, but it's rather an everyday foundation of making your work easy to share and easy to replicate. It gives you peace of mind because effectively having your data under version control effectively acts as a backup. It gives you the freedom to explore new ideas, to try new things that might not work out and backtrack easily. And it gives you a way to more easily collaborate with others, because by having your data stored in these with a system like Git, then others can basically get to that same story and synchronize with you without doing things like, get an email with an attachment with a file name like that, which we have all gotten, right? And we keep appending our names to it and --final, --really final this time again. You can use it for writing your grants. You can use it for everyday research. You can use it for teaching. These screenshots are of a very old interface. I should update them with something more contemporary, but the basic idea applies. This was a course that I taught a long time ago where I was using a graphical interface, kind of a baby version of something like GitHub, much more primitive at the time, that would allow me to have repositories where every student had their own work that I and my co-instructors and my TAs could see. A public repository that had the data for them to access. And repositories where the management team and the administration team could synchronize private data like homework assignments. We use this all the time. Today, GitHub actually offers special tools for classroom management, which I believe have improved. I used them a few years ago. They were already pretty useful, and my understanding is that they've improved a lot in the last couple of years. I haven't checked them out in the last 2 years or so. For me as an instructor, it was very useful to see the history of what the students were doing, and it simultaneously meant that all of the students had their data completely backed up in the GitHub repositories, which was extremely useful and gave us a lot of peace of mind. Now, Git has sort of this reputation, right? That it has a distributed and very abstract model. This is one of the classic XKCD comics. And what we want you to get out of today is exactly not to be in the punchline of this particular joke, right? We want you to have enough actually of that graph theory model, which is less scary than it sounds in the comic, so that you actually don't have to blindly memorize, but rather you understand what is happening, so that help messages, answers that you find online, explanations in manuals, and error messages actually make sense, rather than being than basically being limited to download and restart every time that you have a problem, okay? So I am actually going to give you a few key concepts of that graph theory, but we don't need to talk, we don't need to use graph theory terminology. We're simply going to talk about data that is related to other data that evolves from other data. There's a fundamental concept and a term that you will hear a lot when you talk about Git, and it is the concept of a commit. What is a commit? And it's used as a noun, not as a, well, it's also used as a verb, but it's also used as a noun. The idea of a commit is that it is a snapshot of your data at a given point in time. The details of how commits are structured under the hood don't matter too much. A commit internally has data that describes how the hierarchy of pieces are laid out on the disk, and each of those, each blob of data that is being stored, is actually called the blob, has its own additional data. But the two right parts of the image, you don't need to worry too much about, unless you're doing very low-level operations on Git. The point is, a commit is a combination of potentially more than one file that you're storing at a given point in time, and it represents the state of all of your work at a point in time. Importantly, it is all of your work. A commit doesn't represent these two lines that I just changed now. No, the commit includes that information, but it represents the entirety of your work. So when you look at a given commit, you're looking at all of the data, all of the files, everything that you told Git that you wanted to track is represented in the commit. Now, what is a repository? You'll also hear the term a Git repo, right, or a repo on GitHub. A repo is short for repository, is a group of linked commits. The idea is when you began doing your work, you had a first commit. You put your initial version, the initial version of your data in there. That's the first snapshot. But then you do more work on it, right? Maybe you edit a file, you make changes to it. That new commit derives from the previous commit. We say that it's a child that has a parent commit. That is a new snapshot of your work. And then from that, you can make more changes and have a new snapshot of your work. So as you change your work and you record it through Git, you begin having a linked chain of commits. And that group of linked commits is what's called a repository. Now, technically, yes, computer scientists in the room will like to call this a directed acyclic graph because it is a graph. It's a set of nodes that connect to one another. It is directed because there's a notion of a parent and a child. That notion derives from simply where did you start to make changes. So the changed version is the child, and the original version is the parent. And it's acyclic because there's no such thing as basically going back. Right, there's no way to say the parent is now connected to the child by an arrow in the opposite direction. So in the way a repository evolves, since you're always deriving new work from parents, there is no way to create a cycle in those arrows. And that is technically called a directed acyclic graph or a DAG. You may hear that jargon. It doesn't matter. What we the idea that we want you to have is that your data is in these boxes that are called commits, and they have an arrow. There's an arrow relationship between them. There's a direct relationship within them. Importantly, each of these things is identified by what we call a hash. A hash is a fingerprint of the content of each commit, and importantly, its parent. This line right here is the entire concept that you need to understand, and this is sort of the magic of Git, is the idea that you create a fingerprint called a hash. A hash function is a function that takes a set of input and generates a random looking string that uniquely identifies that initial content. So from a given set of data, you compute this string. There's multiple hash functions out there. Git uses a specific hash function called the SHA-1 hash function that produces these long strings that are hexadecimal. It does, the specifics of hash functions don't matter. The point is, think of it as a fingerprint. But the important trick is that you don't just fingerprint the content. You fingerprint the content and the fingerprint of the parent. And by doing that, each fingerprint effectively links all of the parents together. And so whenever you compute the fingerprint of one commit, you are effectively verifying the integrity of the entire chain of linked commits. The reason is that hash functions, by their nature, change whenever their input changes. So if you change a single character in your data, the resulting fingerprint is going to be different. And because any given fingerprint of, say, this commit includes the fingerprint of the parent, and that one was computed with a fingerprint of the parent, etc. If you literally change one character in the very first commit, that will trigger the changes in the fingerprints of everything after it. So you can verify the integrity. It's not only about sharing and collaboration, it's also the fact that now you have cryptographically strong verification of the integrity of the entire history of a repository. And that can actually be important. For example, if you need to verify that you're about to compile a piece of software whose integrity you're not sure about, you can actually validate whether those fingerprints are correct or not, and Git gives you tools to do that. Now, to close this introduction to these basic concepts, we're going to basically implement Git. We're going to implement Git in Python. So this is a bit of Python code. When I run this code, I am creating a baby version of Git by creating a commit that consists of saying the data in my page. This is the data that I'm committing. The data is a string. There's some metadata, such as the date. Git always stores a lot of metadata about your work, things you didn't type. And what we're going to do is we're going to compute the fingerprint of all this data, my original data plus my metadata. And we're going to print that the underlying SHA-1 objects don't have automatically the kind of text representation that you see from Git, that's accessed by calling the hex digest method. And if we print that, we'll see this is the hash of the parent. And now, when we do new work, we have, on a different day, we have now more text that we've added to the paper. It happened on a different date. And this is the Git trick, that the new hash of the child, the very first one is unique and special in that it has no parent. This is called the root node of the graph. But after that, every new commit is compute the fingerprint of the data plus the fingerprint of the parent, right? We have the parent here, and we turn it in, we call the encode method on that to get a text representation, a simple text representation of that hash. And now we have a new hash, a new fingerprint. This chain of fingerprints represents this data. And if you see, if I'm going to re-execute that first cell multiple times, and you see that the hash doesn't change. But if I make a single change to the text, the resultant hash changes dramatically. It's the same one. It's deterministic. It's not a random function, but it changes with a single character change. It changes dramatically. And if that one changed, then the next one would also change because of the linking of fingerprints between them. This is the essence of Git. We're not going to do any more low-level theory, but I have found it very useful to understand that at the end of the day, all that Git is doing is tracking the relationship between blobs of data that are fingerprinting and labeling them. And every complicated command that you see in Git at the end of the day is an operation with these blobs and labels on these blobs. So before we actually get started using the real Git, so this is a toy baby implementation of the core idea of Git in Python, just to show you that something that actually the core concepts are not that complicated, and even their implementation is straightforward. But now we're going to be using the real tool, the real Git, and for that, it is important that we configure Git. So now I'm going to do exactly what Fernando had shown, which is to have my terminal next to my display. And we're going to configure Git by issuing these commands. You can copy them from here. So if I copy here and I paste here, whoops, I accidentally hit copied the return. So when I pasted, I configured it as your name. So I'm going to up arrow and type back, Fernando Pérez. And the git config command stores configuration information. If I say git config -- global, that means I want this information to apply to all of my Git repositories. Git will store that data in a file in your home directory on the system. You can also configure things without the -- global flag, and that will configure specifics for the current project, which means you're free to have basic global defaults that you want to apply all the time, and configuration parameters that are specific to any given project. And so similarly, I'm going to do user.email, and I will, whoops, that's not my email. That's my email address. And so now if I type git config -- global -l lists all of my current global configuration. I also have this other flag that I had written before, where I tell Git to use colors in the terminal. It's very handy to see information from Git in color. So you should, at the very least, do this, because if you don't, Git is going to complain when you use it, okay? So next, we're going to get into the first concepts. After these introductory concepts, we're going to get into the first parts of the workflow. So we're going to open the first tasks notebook. I clicked on this, and it takes me to the first tasks. And so now we are actually going to execute all of these commands. Here. So in here, I am in my home directory, which is exactly a good place to be in to do this. If I simply type git, I get information from Git about some of its basic commands. And the first thing that we're going to do is to create an empty repository in here. So I am going to type, these commands were typed in there using the kind of tricks that Fernando already explained, but I'm not going to, in order so that I can basically reproduce the entire sequence and know that it is correct. But we're actually going to type these things at the command line, and I encourage you not to copy and paste, but to actually type so that you get a little bit of muscle memory practice in this. So at first, I'm going to make sure that I don't have an existing test directory there. So I'm going to rn-rf test removes a directory called test if it existed, because I'm going to create a directory called test by typing git init test. So when I type that, Git tells me it initialized an empty repository in a folder called test. And if I look here at my home directory, I now see a directory called test, which wasn't there before because I had just deleted it if there had been one. But Git, so let's go into there and let's look at what's in there. It seems like it's empty, but Git said that there's something in there called .git. So if I type ls-a, ls-a tells the shell to show me everything. By default, Unix shells do not show, they hide files and folders that begin with a dot in their name. They're used basically for configuration and kind of system level operations. And so there's a convention that if a file or directory begins with a dot, it's not shown. -a shows those. The .git file is the file, the directory.git. Let's list that with -l, which gives us more details. This information right here shows you the permissions, and the first letter here says that this is a directory. This is not a file, it's a directory. That's what the D means. So what Git did was it created a directory in there, and that directory contains its own data. We're not going to dive deeply into what's stored in the .git directory. Suffice to say that if you delete the .git directory completely, you turn a repository into a plain old folder. So if you ever have a big repository that has whose .git directory has a lot of history and you just need the files on it and you don't need all the Git data, you can literally just do rn-rf.git and your repository becomes a plain old folder on your computer. So now we are going to put the first bit of data in there, and I'm going to do that at the command line by just typing this, echo my first bit of text. And I'm going to redirect this to file1.txt, okay? So I now have a file called file1.txt. That file is, this is an operation that says, print this bit of input of information, but send it to a file on disk. Now, Git doesn't know that I care about that file. We need to tell Git that this will be part of these snapshots that it fingerprints and remembers. So after you have a file, and by the way, I want to show you that now the file manager in there, if I go to the test directory, the file manager sees that, and I can actually edit that file. If I double click on it, I can actually edit that file. Let me put in here the file so that we see it. So now I am going to tell Git, I want you to know about this file and I want you to track it for me. We do that by saying git add file1, and there I use the tab completion that Fernando spoke about. By typing git add file, now Git says, okay, you want to know about this file, I will fingerprint it, store it, and keep track of it. Git status is the next command that you will want to get familiar with. It's a command that you use a lot. And the git status command shows the following information. It says that there's a new file called file1.txt, and there's also something it is not tracking called .ipynb checkpoints. And the .ipynb checkpoints is a directory that Jupyter creates to track notebooks and other things for backup purposes. And Git doesn't know about it, which is perfectly fine. We don't need Git to know about this. And this is why I wanted to configure the colors before. So that different information is shown in different colors. It's very handy. Git shows a lot of data, and so color helps. If we now record, in order to now actually create a commit, we're going to use the git commit command. And in order to keep things simple, we're going to, at the beginning, use git commit, typically with the following flag, -a. The -a flag tells Git, please commit every change that I have lying around to any of the files that you know about. It turns out that you can use Git in a more fine-grained way by committing only specific things that you have said you want to commit. This is a process called staging. And so you do your commits basically in 2 steps. You tell Git, these are the things I want you to, these are the changes I actually want you to know about, and then you put them in. It requires a little bit more management. So by default, we're going to use for now commit -a, which says just commit all my changes. Later, as you get more familiar, you may want to become a little bit more granular in that process. And then we're going to always put what we call a commit message with the -n flag, which says, what did we do? And so this was our first commit. And by doing that, we are making a commit. What Git did was it said, this is the root commit. Remember, we said the very first one has no parents. It's special. We called it first commit. There was a file that changed, one line changed. It was created. It's file1.txt. And this is the fingerprint that it computed. Okay, so that's what Git did right there. It fingerprinted it exactly with the same hash function that we talked about, including the data that we put in and some metadata such as when we did it, etc. What kinds of permissions the files had, everything that Git would need to reconstruct this data in a different location or a different computer. Now, if we want to see what we have done so far, the next command we're going to want to know about is called git log. And git log is a command that tells us successively what it did. And here, importantly, this is that fingerprint in its full glory. Typically, you can abbreviate these fingerprints to just their first few characters. And that's why Git, by default, only shows you 7 characters. They're very long, but they're designed to change a lot with any changes so that the first few characters are enough to uniquely identify one of these fingerprints. But with log, you see all of it. This is some of the metadata that it's stored. So here you see the importance of having done that configuration at the beginning. This is the commit message that we wrote. And these labels are important. Gradually, we're going to build knowledge about these labels, but at least I want to point out 2 things. The first one is the default called master. That is basically this line of history that Git will track is called the master branch. We're going to talk about branches later. Basically, you can have multiple versions of the history of your project that evolve independently. The default one that Git creates when it initializes, when it just gets started, is always called the master branch. And head is a special label of the current commit in that branch. So remember when we saw these, let me put this right here, when we saw these commits that evolve, right? A branch is a sequence of these that are linked to one another, and head is the current one that we're sitting on. So head is the current command that we are currently working on. So if we have made 3 of these and we're down here, head is this commit. And so as we add new commits, which one is called head changes. And I know we're starting to obviously run a little bit behind on time, as always happens. So we're going to continue, but I'm going to try to be mindful of the time. So now let's say that we do a little bit more work. And now that we have the advantage of working, of having a text editor, I'm going to actually use that to add more work to my paper, right? So you see, as I type, this dot up here indicates that the file has changed. When I hit Control S or Command S on a Mac, it saves that file, and that data is added to the file is written to disk. And so now that I've added some more text, we can also do that at the command line by appending to a file. This is what that command looks like at the command line. And so if I now type git diff, which is the next command we want to know about. So status tells me how are things currently. Log shows me what has gone into this permanent record of Git. And diff tells me what is currently different between what Git already has recorded permanently and what I have just done to my files. So I'm going to clear my screen and run git diff again so that you only see the output of that, okay? Because it is important to at least have a basic understanding of the information that Git is showing you here. It's described in the tutorial, but I'm going to explain it. There's a very specific format to this output, and this was partly why having color was important, because there's a lot of data that comes out on these things. And so the basic information that Git diff shows you is the following. It says, this is a comparison between two versions, version A and version B of the same file. You might say, what do you mean two versions? Well, remember, Git has a snapshot of your work. So internally, it has a version of that file already stored. And there's another version, which is the one I'm working on, where I'm working on the disk. And so Git is comparing its internal version to the one that's sitting, that I actually am working on. And what it says is, around these lines, so this information, these @ signs show location on disk. So around this location, there's been some changes. The minuses would, on the left will refer to the internal version, and pluses refer to what's new on the version that we're working on. And so there's no, we didn't do anything, we didn't delete anything, so it doesn't need to show us that there was something in the internal version we're not seeing, but it does show us that the working version has something new, and it shows it with pluses, and because we told it to use color, it also shows it in green. And so you get pretty quickly used to reading these things and to basically know what is new, what was deleted and what was added to text files. This is also why it's tricky for binary data, because it's not so easy to represent line by line changes, say, to an image or to a Word document or to a Jupyter notebook, actually, for that matter. But it is important to become familiar with the basics of reading these things, because it's kind of a daily occurrence. So the sort of what I call the cycle of Git virtue is you work and you commit, you work and you commit, you work and you commit. So here we're going to make another commit. So if I now say git commit -a, I'm telling Git all the changes, whatever they are, send them in with a message called more work. And I want to show you what happens if you don't put -n. If you don't put a message, this is what happens. You end up dropped into an editor. We don't have time to explain how to do this. This is why we're handling the messages explicitly at the command line, so that you don't get dumped into this. For those of you who are used to VI, this is the VI. The default Unix text editor is VI. It's not a particularly easy tool to learn how to use, though it's very powerful. I personally don't use it, but I want to show you at least how do you get out of it. If you end up here, the way you get out of it is you type :Q! Which says get out of here no matter what. And then we're back at the terminal. And I don't have time to give you a VI tutorial. That's a little bit outside of the scope of what we can do today. And I'm also not a VI expert. My default editor is a different one. You can configure Git to use any command line editor that you want. And on a local system, even graphical editors. We're actually working on making it possible for Git to access this editor by default, but it turns out it's a little tricky, so we can't do that right now. So more work. But for now, if you type your commit messages at the command line, you'll be fine. And over the week, we can help you set this up in a more persistent, in a more kind of comfortable manner with a tool that you're happy with. So that is what that cycle of virtue is. And if we now ask Git for the log, we now see that there's two commits. This was the first one, and there's a new one. And you see that now this is head. Head is not here anymore because we've added a new block. So the Git shows the commits in reverse chronological order. Sometimes it's very handy. Now I'm really going to go quickly because I want to wrap up this part to leave room for the interactive exercise. But this is something that's very handy that I use a lot, which is git log with a couple of options. To basically shorten the information that Git shows, and to show a graph. This is particularly useful once a repository begins getting complicated and there's multiple branches evolving in parallel. This detailed version is not very useful to get a big picture perspective. And so with these options, you get a summary of each commit, but you get the overall structure of the work, and it's very, very handy. It turns out that Git supports what are called aliases. So I actually have a Git alias called git slog, which I will create here. Copy. let me paste here. If I type git config and I say I want a global alias called slog, which is short for log, one line topo order graph, those same options. Now I can type git slog and I have this short version of the log. So you can basically create your own convenience aliases to use Git in the way that you find most handy. Now, a few more things that we do need to cover. What happens if you need to remove a file or rename a file? Remember, Git is internally tracking those things. So if you simply go, say, to your file manager and say rename or delete this file, Git will get a little bit confused because internally it is tracking those files because you told it with git add. We told it with git add that we wanted to track those files. So if we want to do that, if we want to rename a file in a way that Git understands, oh, file 1 has a new name, we need to use a git command that says git move file 1 to file new name. And now when I type git status, it now says, oh, this file has been renamed. And we can commit again. So git commit -a -m new file name. And now if I type git slog, I see one more, this new commit, and it does show a summary of the commit messages. So now you see these fingerprints evolving, and these are all parent, child, child. Okay? So the next concept that I want to introduce is the concept of a remote repository. A remote repository is the following. First of all, let's see if we have any remotes. Nope. Git remote -d says, show me any remotes that I have. What is a remote? A remote is a copy of the Git repository in a different location, stored somewhere else, for example, on GitHub. And so what we're going to do is we are now going to create a Git repo. Actually, I think that's actually done in the interactive exercise, exercise next. So we will do that in the interactive interactive exercise that comes next, is managing remotes. But the idea of a remote is that now that we have this structure right here, where all of this data is copied and tracked locally, we can host that same information on a different machine. And if that machine is accessible by others, then it allows them to access the same history with the same fingerprints and reconstruct exactly what we had been doing. And that's exactly how the GitHub network of collaboration grows, basically from locally stored data to replicating that locally stored data with all of this internal structure on a different server, and with others having permission to access those servers. So in the interest of time, I think I'm going to hand it over to Daniel to do the interactive exercise that actually does cover using remotes up on GitHub. And that way, because these things are much better learned by you playing with the tools than by us typing in front of you too many things. But hopefully this gives you actually a mental model of what is happening under the hood that will be useful so that you're not only memorizing concepts, but actually understand what's going on. So I'm going to stop my sharing and I'm going to hand it over to Daniel right now.
Hi, everyone, and thanks, Fernando, for the introduction. So what Fernando has described is some of the things that you would need to use if you were kind of doing a single user workflow with Git, where if you had one repository, you were working on it by yourself and you wanted to sync it to somewhere in the cloud like GitHub. So one of the things that we're going to have to do in this workshop is work with each other, where things get a lot more complicated. So Fernando talked briefly about remotes, and I'll show a bit of how you can kind of introspect those and add new ones. But the main thing I wanted to show is something that's going to happen, which is when you have two people who are contributing to the same repository, and when they try and commit a lot of things on top of each other, and you can create a bit of a mess. And then I'm going to try and show you a way out of that, which is to use branches and merging. So I realize a lot of this stuff is kind of a fire hose of information. And like, again, always feel free to ask us about it. I've been using this thing for years, and I've been working with students, and students I've been working with for years, where we're still like learning new Git Kung Fu with each other. So what I've done to demonstrate this, and I'll start sharing my screen. Unfortunately, so this is a topic that's a little kind of challenging to demonstrate by yourself. So I'm going to do my best here. And so what I've done is I've created a new GitHub account. My usual GitHub account is Dan Shapero, and I've created one that is Dan Shapero's sock puppet. And I've created a little repository called Fibonacci, where all I did is make one Python file that has something that calculates the Fibonacci sequence in a very, very bad sort of a way. Now, what I've done to try and demonstrate how you actually collaborate with others is I added my original GitHub account as a collaborator. And I can show you how to do that in a sec, but I just want to breeze through this really quickly so we can see what the actual problems are. So what I've done is I have two terminals open here on my machine. Let's clear that. So the one on the left is the sock puppet account, and the one on the right is the actual Dan Shapero account. So just to go over again some of the things that Fernando talked about, if I do git log, I can see what the very first commit was, which shows the hash and the description and everything. And you can see what's inside that file and so on and so forth. And at the end, Fernando was talking about remotes. So git remote, if I do that, it just says there's one remote called origin. And if I do git remote -v, the V stands for verbose, which means it's going to show extra information. Then it'll show the origin and what the web address of that repository is. So I've given from the sock puppet account access to my Dan Shapero account to that repository. So now what I want to show you is what happens if, imagine these were two completely different people and they were friends and they were trying to work together on the same repository. And they're kind of, they're not always talking about what it is they're doing. So I'm going to say, imagine for now that, say, this sock puppet account wanted to create a README. So if people found this repository, they would know what it does. Which, if you didn't know, Fibonacci sequence was first used as a model for studying the propagation of rabbits in Fibonacci's garden, which he was very displeased about. So again, if I do status, I can see that there's an untracked file called README. Whoops. So I'm just going to break that up a bit. If I do git add, it'll say that this change is to be committed. And now if I do git commit -m, then it shows that my branch is one commit ahead of origin master. So this is something new that happens when you have remotes. It'll tell you whether your local copy is in sync or out of sync with the remote copy. And this is really useful information. So now I will do git push, and it'll ask me for my username and password. And it'll sync it with the remote. So if you see the log, we can see both of them. Now what I'm going to do is show you what happens if we have another account that's trying to push to the same repository that hasn't fetched all of those changes. So let's suppose Dan Shapero over here, and not the sock puppet, looked at this and said, we also need to tell people how to use this thing. Really what we should be doing is adding a doc string. So I'll, again, add those changes, commit them. Now when I do push, it'll say rejected. So it gives you this long error message that is a little cryptic. Failed to push some refs. Updates were rejected because the remote contains work that you do not have locally. This is usually caused by another repository pushing to the same ref. So that's a bit of a problem, and there's a good chance that you'll encounter this. So what do we do about it? And this is where branches come in. So one of the things we found last year when we were teaching this is people were so excited to get into the scientific part, and they didn't want to bother with all this branching stuff. And that's totally understandable. But it's going to help you. I think it's going to be really helpful for you when working with each other better. So I'm going to do a bit of magic here. I'm going to, don't overdo what I'm about to do. I'll explain it. I'm doing a hard reset to an older commit. And now I can see that I'm just back at the very first one. So this is a way of rewriting history locally, which I have to do if I want to show you what the right way of doing this is. So what I could do instead is I can create a new branch. So if I do git checkout -b, that'll create a new branch, and I'll call it docstring. And if I do git branch, it'll show you what branch you're on right now, which is called docstring, and any other branches, for example, master. So within this branch, I can, create new commits. And once again, git add. So now I can see that there's this one commit from origin master that's synced to the head. And now I can see that I have this other commit that is on this new branch called docstring. So I want to show you a bit about how you can view all the branches. So before we talked about pushing your own commits locally to a remote. So you can also push branches to a remote. And I want to show you what that looks like in the web interface. So to do that, we have to do something special, which is pass some extra flags. So normally if you do git push and you're on the master branch, it's going to know, oh, I want to push to the master branch. But if I'm on another branch, then you have to give it a little kind of extra information about where to put that. So git push -u, the U is for update, followed by the remote, which is origin, oh, and the branch, which I don't want to be master. I want the branch to be docstring. Oh God, I've forgotten it. I knew this would happen. Ah, there we go. Okay, this also illustrates something. I've been using this for years and I forget what the shell commands are all the time. And I usually just mess them up and then have to try it again. So there I couldn't remember whether it was supposed to be a slash or a space. It happens to all of us. Let's see what this looks like now. So in the web interface on GitHub, you can go to commits. So here I can see there was the very first commit. Then there was one where we added a README. Now, if we also look, there's this extra tab next to it that says branches. So first it shows the master branch, which is pretty much always going to be there. And then there's this other branch called docstring. So these numbers here show you how many commits that branch is behind master and how many commits it is ahead. So what I did in the terminal is I just started from the very first commit. I entered a new branch and then I added a docstring, but it didn't have all the commit from the README. So there's another way to view these that I find pretty helpful. If you go to the Insights tab, and then you go to Network, then it shows you this handy graphical view of all of the branches in that repository. So there's the very first commit, the commit to add a README, and the black line is usually master. And then there's a blue line that shows this other branch branching off with this commit to add a docstring. So now what happens when we actually want to sync that extra docstring branch back into the master? So this is where the merge command comes in. So one thing that we'll talk about conflicts in a little bit. So what the merge command does is it pulls in commits from other branches, or in some cases, other forks or other remotes. So if I do git merge master, and what that's going to do, oh, I forgot a step. So the first thing I'm going to do is git fetch origin. What this is going to do is just talk to the remote and say, have there been any changes since I did anything last? And there's been no changes on the docstring branch because Dan Shapero is the only one who's been changing them. Now what I'm going to do is I'm going to check out the master branch. Now, since I've done a fetch from origin, it's given me more information. Your branch is behind origin master by 1 commit and can be fast forwarded. So if you just do git fetch, all it asks is, have new things happened? Git pull tells Git to actually fetch all the new things that have, or sorry, to actually pull down the new things that have happened. Now if I do git pull, it'll show me that there have been changes to this README. And if I do git status, it won't give me any weird messages that say we're ahead or behind. So now I have the remote copy of master in my local copy for this user, Dan Shapero. And now we're going to get to the syncing part. Git checkout docstring. And now I'm going to do git merge master. So when you do merges from other branches, it'll drop you into a text editor before, which Fernando had talked about if you just do git commit without specifying a message on the command line, then it'll drop you into Vim and tell you to type one in. So it's the same thing when you do merges, because often if you're merging, like this is sort of more for the power users, if you're merging in a whole bunch of branches at once, you want to be able to put in special messages that describe what it is that you're about to do. But I'm not going to do anything special, and I'm just going to leave this message how it is. And probably one of the most important things you can know is how to quit Vim, which is a colon and a Q. Now let's look at what the log says. So here we had everything from before that was on the master branch. There's the first commit, there's adding a README. Now what this has done is it's put my docstring commit on top of the commit for adding a README and created a merge commit. So it'll say that my branch is ahead of the origin by 2 commits because there was the initial one where I added the docstring, and also on top of that, I created a merge commit. So now I'm going to push this just so we can see what it's going to look like in the web interface, and you can see the graph again. Right. So now the graph has changed a bit. So it has this funny little arrow that shows a merge commit from master into the docstring branch. And now we can go back and merge docstring back into master. So this is one way to sync your changes. So here, I'll do that right now. Git checkout master. So it shows only one change. And now when we push, everything is all synced back in. And likewise, now we can go back to the sock puppet account and just do git pull. Oh, that's a funny error message. I'll deal with that later. So this is one way to kind of make your life simpler when you're working with other people. Generally, you'll all be working on different branches. Now, one thing that's worth noting here is one user, the sock puppet, was creating a README, and another user, my original account, was modifying the Fibonacci notebook. So when you're working on 2 different files, it's very easy to merge everything back together. You can have more problems that will create what are called merge conflicts if, say, we were both editing the Fibonacci file. So unfortunately, I don't have enough time to cover those right now. It's something you'll probably run into, and you should totally feel free to ask us if you do have one of those. But it also illustrates a better point of you're all going to be setting off and creating your own projects. And one thing that's really good just in software engineering is to try and structure all of your projects in putting different functionality in different files and modularizing them in such a way that all of the people working on it can more or less work on the different parts independently. Designing things so that you don't create conflicts when you're merging all your code back together. That isn't always possible, and there will come a time in your life when you have to resolve some really awful, hairy merge conflict. But you know, an ounce of prevention is worth a pound of cure. I think that was most of what I wanted to cover. There are a few other things related to, so there are other ways to do this. You'll probably hear the term rebasing at some point, which can be a nicer way to do things to produce a cleaner history at the end. But I think it's a good bit harder to use at first. So from what I understand, I think we're just going to stick with the branching and merging workflow. And later we can also talk about forks and things like that. So hopefully this isn't, I think we're going to repeat a lot of these ideas again. So hopefully this was at least informative and you heard some of the words and internalized a bit of it. But again, always feel free to ask us about this. And I think that is all I had planned. And I'll hand it off.
Thanks, Daniel.
Thank you, Daniel. Sorry, folks, that I think we're basically running into the time, and we want to give people a chance to take a break. We were just discussing that in the next tutorial, which is the Ipython one. There's a little bit of intro of just the basics of using the system and the user interface that are honestly pretty straightforward. So I think what we'll do is we'll eat a few, maybe 10, 15 minutes max of the Ipython tutorial. We'll eat into that to at least kind of refresh some of these concepts at the very beginning, and then we will continue with Ipython and Jupyter, because it is true that these concepts can be tricky to wrap your head around the first time. I'm also happy to hold a separate sort of office hours joint practical tutorial later today or tomorrow. We can coordinate on the Slack channels for folks who for whom this is new and they want to practice a little bit. They're running into weird error messages. They want to understand what they mean and how to get out of those situations. I'm more than happy to hold one or more sessions of that kind, and it could be useful to do it even later next week as you begin actually working and you run into more complex situations. And we're happy to help you with that. So we'll cover a little bit more, but we don't want to eat into giving you a chance to take a break, or if you had something already scheduled for the next half hour, and then we want to give people a chance to do that. And we'll see you again here in 30 minutes. Thanks, everyone, and we'll be back in 30.
The recording started?
There we go. Okay.
Good, thanks.
So thanks, everyone. Welcome back. We just had a bit of a chat with the instruction team, and we've decided to take a moment to answer a couple of questions that have come up a lot about Git, and actually finish up a few more Git-related concepts, eating a little bit into some of the introductory material for the Ipython one, and then we will switch gears into that. So the first thing is that a number of you, when you had already cloned the repository and maybe played a little bit with it, and when you did, when you tried to get pulled, you got an error message like oh, I need to share my screen for you to see that, I'm sorry. When you tried to share your screen, you got an error message like what's on my screen saying git pull, updating, etc. No, you can't. You have local changes to this file that would be overwritten by the merge. It turns out that I had made some changes here. I typed my changes here, and that now the problem is that Git wants to update that file because new content came into that file, and I have my own changes in that file that are that conflict with the data that would be coming in, and Git doesn't really know what to do there. It's particularly tricky with a notebook because the notion of merging changes into a notebook is a little bit complicated, unfortunately. We don't have the smoothest workflow. We're working on that, but it's not perfect. There's a variety of reasons why that I'm not going to get into right now. That means that right now we need to figure out how to be able to actually incorporate the changes that are coming from the repository. So a simple way to do it, it's a little bit manual and clunky, is to simply copy the file that has the local changes to a different name that Git doesn't know about, reopen it from there, and then let Git pull in the changes without conflict and manually basically moving over any notes or any other content that you have. It's a bit clunky, but it gets the job done. In general, if you are pulling in material from a tutorial, it's best not to modify those same files since constantly there will be new content coming in. What I'm going to do is actually tell Git, you know what, I don't care about my changes. Just let's just get a copy of the file the way you had it, and then we'll move on. So I can do that by saying git checkout the file that has the problems, this file git intro concepts. If I say git checkout, what I am telling Git is, oh, from the file that you have stored internally, get me that copy and put it right here as if it was my copy. So when I do that, this file, and it's best to close it first. I should have done that. If I reopen it, you'll see that that line that said my changes is gone, because I told Git, get me the copy that you had internally stored. And now when I do git pull, the changes come in nice and happy, and those changes to that document, git intro concepts, do come in without a problem. So this is a quick way. If you don't care about your changes, you can tell Git, give me the internal copy you had back into work, and let's continue. If you really do need to make a merge, with notebooks, as I said, it's a little bit trickier because they're not plain text files that Git knows automatically how to merge, so there are tools for that. Or one easy option is to make a copy of it manually, pull in the changes, and copy them back. But it is true that the workflow for merging on non-text files, and that applies to Jupyter Notebooks, but also to images, if you have a Word document, etc., is a little bit tricky. And for those, communication with your team remains necessary. Basically, coordinating with your team who is working on what, so that you don't step onto each other's toes, is absolutely necessary. Git is very, very good at managing the data, but it doesn't substitute human communication in your team. So this was one of the things that did come up. Now I want to, Daniel gave a very quick introduction to the notion of having more than one branch, and I want to illustrate some of those concepts from the first tasks notebook, so that you have sort of, again, what we want to do is give you a conceptual idea of what these things are, okay? And so what is a branch? A branch at the bottom internally in Git is actually nothing fancy. It's just a label. Think of it like a Post-it note. We have this notion that we have various commits that are identified by their fingerprints. Right? In this case, each of the green boxes is just a commit. It represents everything that's there. So this is the state of your work as you go over in time. And we said that by default, Git calls the first line of development the master branch. Master is just a label. Think of it literally as a Post-it note that you move, and as new commits arrive, it begins being this one, and then this one is master, and then this one is master. It's just a label so that you can refer to to that commit by something a little bit more human, memorable than a hexadecimal string. Now, you can have more than one branch at any given point in time. And so if you say, I want to also call this the testing branch because I'm going to begin doing new work, you can make a new branch. And all that Git does is it adds a second Post-it note. It adds a second label to that same commit. So now the same thing can be referred to as master and testing. Initially, these two branches are actually contain the same data. They're just two labels pointing to the same data. And remember, when we looked at the log, we saw that there was this label head, right? That label head points to the current commit. And that label is a special label that moves along with your branch and tells you this is where you currently are working. There may be multiple branch labels, but there's always only one head. Head is this is where you happen to be. And that potentially complicated graph that grows over time and that may have more than one branch, as Daniel was showing, head is this is the one you're working on. And so when we make a new branch and we start making new commits on it, then that's the branch that grows and head moves with it. So for example, in this case, if we had master pointing here and we created a new one as in here, and then we make a new commit, if this is the branch we're working on, that new commit now moves, but master stays where it was because we were working on this one, not on master. So this is how histories begin to evolve differently. So in this case, C3 is a new commit that was derived from C2. Now, somebody else could be working on master and say, I'm going to also make a new commit, starting from where I was on C2. So now that becomes C4. So C2 now has a new child, C4, and a second new child, C3. Both of these can contain different data. And this is how branches begin growing. They're just labels, and they continue moving as work is done under that label. And you can hop between labels as needed with the Git branching commands. Now, if at some point you say, well, I did new work on this IS-53 branch, I did new work here, I added this bit of data, and I also added this bit of data. Now I have a history where master has this line of development, and this ISS53 branch has this line of development. But I might want to say, well, now I want all of that work to be a single line of work. These changes, I want to incorporate them back into our main line. These were fixes for something that was independent from this, and I want them merged. This is what Git will do. When we say, I want to merge that command, that data into master, what Git will say is, well, let me look at the data that was here. Let me look at the data that was here. And as long as those two sets of data do not overlap, which Daniel pointed to can cause conflicts, and that is something that is best avoided with communication, but can be managed if need be. Then when we merge, what Git will do is actually bring all of those data together into a new commit that now actually has two parents. So this is how these graphs grow over time, okay? So we don't have, we don't want to eat too much into the Ipython and Jupyter tutorial, but we at least wanted to illustrate, what the concept of branches is, and that at the end of the day, if you're ever confused about these graphs, think of them as branches, as strictly labels on otherwise the content and the history of your work. These labels, you can make as many of them as you want. You can delete. Deleting a branch is nothing but deleting that label. So if your history has too many branches, you can get rid of them by deleting those labels, and Git will stop showing them to you. It doesn't throw away the data. So for example, if we here say, I'm not interested in tracking that label ISS53 anymore, and I delete that, the data on 5.3, on C3 and C5 stays stored, and it's connected to the data on C6 that depends on this line of work. It's just that you don't need to remember it by name anymore. So branches are really just names that you use, mnemonic names that you use to track different parts of this evolving graph of work that you create and manipulate. And I find it very useful. There's a little bit of an exercise here, which is very similar to what Daniel did, so we don't need to repeat it. But I find it very useful to think of branches in this way as nothing but labels on the underlying structure. And then every operation, and operations such as what Daniel referred to of rebasing, which we can discuss later in office hours, or we will encounter later in the week, are the kinds of operations that seem a little bit mysterious at the command line, but if you think of them in terms of what is happening here, in terms of moving pieces of these graphs and repointing the arrows to other places, they actually are conceptually fairly straightforward operations, even if some of the messages at the command line may appear confusing.